worked on many timber structures, then I was even more fortunate to spend 10 years of my career working as Professor of Timber Engineering at the University of Bath. I retired from Bath just over 3 years ago, and I keep interested in timber with my little company, providing consulting and teaching and research. So Wen-Shao asked me just to put in a few slides to say why timber is such a significant material in construction at this time, and I feel it sort of speaks for itself, but Wen-Shao says we must keep reminding people of how wonderful timber is. And the first thing I would say is that what's been so good, especially about the last 10 or 15 years of my working life, has been that timber is a material that's modern and developing. And if you go back 20, 30 years, people used to think that timber was an old-fashioned material to work with. It was something we used to use in the past. But with so many new products coming into the industry, and because timber is such a sustainable material, it's very much the material of the future. And you'll always hear people saying, well, what do we do when we have used up all the trees? But of course we don't use up all the trees. There's plenty of room to plant more trees. This country is only 10% forested, as compared with Germany that is 35% forested. So even in this country we could plant a lot more trees, and the same is true of other countries. So it's a material that is sustainable, because when used from certified sustainable sources, every tree that's taken out of the forest will be replaced by at least one other. So it's a material that will always be available, and being available, it's a material that helps us to cut greenhouse gas emissions, because we're not producing huge amounts of carbon dioxide in the manufacturing process. There's obviously some emissions in sawing and preparing timber, but as compared with heating up limestone and clay to make concrete, or forging steel out of ore, the emissions are tiny. But even more than that, because it's coming from renewable resources, then we know that when working with responsibly sourced timber, we're constructing without depleting the Earth's resources. So we've got the benefit of reduced greenhouse gas emissions, but in addition, we're not depleting what we have. So from the point of view of greenhouse gas emissions, there's a double potential with timber. We know that for every tree that we take out to use in construction, if we replace that with another tree, so we create space in the forest and replant, then that tree will continue to take carbon dioxide from the atmosphere and hold it within the forest. But the tree that we've taken out, we can use in the building, and that in itself becomes a store of carbon and holds the carbon dioxide that it's taken from the atmosphere in its growth, so that we have a double contribution of benefit in terms of carbon dioxide. And it's very simple. In growing trees. The photosynthesis enables carbon dioxide from the atmosphere to be combined with water from the ground with an input of energy from the sun, and we get a complex hydrocarbon, and we release oxygen into the atmosphere, and we have a potential of energy held within the wood as well. This is easily, I've given these slides to Wen-Shao, so if you want, it's so often quoted that carbon dioxide and water give that complex hydrocarbon and oxygen, and this is a simplified expression, but it's basically covers the process, and it's frequently quoted that 1 ton of timber fixes 800 kilograms of carbon dioxide. But the way to get these figures is to sorry, 1 cubic meter of wood, which is around half a ton of wood, fixes 800 kilograms of carbon dioxide. It's simply a question of balancing this equation with the molecular weights, and you get that answer. It's so frequently quoted, but that's some numbers that you can put to it. And this is the way that it's usually portrayed. I really like this poster, which Wood for Good used to use about 20 years ago, which simply said, let's siphon the carbon out of the atmosphere and turn it into houses. So you can work out the numbers, or you can simply think, well, let's just take the carbon dioxide out of the atmosphere and turn it into houses. So that's a little promotion for the use of wood. And the rest of the lecture, I'm going to talk about a very particular use of wood, which is the timber gridshell. And this is an unusual form of construction, but it's a form of construction that can offer you huge creative opportunity architecturally. So, timber's a natural material. What are the properties of timber? It's strong in compression along its length, and it's weaker in bending, but it's very predictable, and it carries bending loads very effectively. But for the timber gridshell, another property that's needed is the fact that when you take wood and twist it, it's actually very weak when you twist it, and that for timber gridshell construction is a real opportunity, because that enables you to lay the wood out as flat on the ground, and if you allow so if you take one layer this way and place another layer over the top of it, and hold it in place at the nodes so that it doesn't lose its geometric shape of the timbers relative to one another, but you allow the nodes to rotate, then you can manipulate that flat double layer of timber into a doubly curved shape. That's because and if you, why do you do that? Well, because a doubly curved shape gives you a shell type of structure, which gives strength and stiffness, it allows forces to go through the surface of the wood rather than just work in bending, and that makes it very structurally efficient. You can create big spaces, and using this timber gridshell method, you can do that very quickly, and actually, given the complex shapes that you're able to create cost effectively. Not a great number of grid shells have been built. Why is that? Well, because you have to know something about how to do it, and not so many people know about. You'll know a lot more about it after this lecture than a lot of other people do. In the past, these structures have been difficult to analyse structurally, but now that's not such an issue because computer power is readily available. You can make grid shells in steel and timber, but the timber grid shell technique is this very special technique that enables you to take a set of standard components and turn them into a complex shape. So if you use other materials, you can make this type of shell structure, and this is a really good example of a steel shell structure, but you can't use that technique of laying it out flat and manipulating it into place because the steel is too stiff, particularly in its twisting strength. So the way that steel grid shells are made is to fabricate all the pieces and weld them together. You put up a scaffolding and you build it in situ on a scaffolding, and that can be done. This proves that it can be done, but it's complex. It needs very sophisticated fabrication methods and is extremely expensive. The timber grid shell can be made in that way, and you can certainly make a timber grid shell structure using by putting up a scaffolding and building it up to nodes progressively. It can be done very easily. This swimming pool structure in Scunthorpe was done with a minimal number of props, just progressively building the shell out into space, but it was still needed to be propped and needed to be put in piece by piece. What I'm presenting here today is what's often called an elastic or a strained grid shell, where you make a flat mat and then you manipulate it into space. So all the pieces are standard pieces. So here's the flat mat, and because the nodes can rotate, so it starts flat on the ground and it's progressively bent into shape by changing its support, and in doing that the nodes rotate into a diamond shape from square into diamond, and the timber twists over the surface till eventually you have complex doubly curved shape from a set of standard components. The first structure to be built like this of any size, there were a few preliminary structures before the Mannheim structure as prototypes, but the Mannheim Garden Festival grid shell was the first and is still the largest timber grid shell to be built, and after that a number of others examples given here. More recently, I've in the last 5 years or so, maybe this has become more and more popular with architectural departments for making small prototype shells, because the components are very easy to prepare, and architectural departments often have a considerable amount of manpower in the form of students. It has actually, this is an example from Naples, from an architecture department in Naples, where they built a small gridshell in the university. And this is another one. When I was working at the University of Bath, Dragos Naicu from Romania made contact with other people, particularly Romanian people, but also people from Denmark, and they set up a workshop in Cluj in Romania, and they built a pavilion. As part of that project, the output of this was published in the World Timber Engineering Conference paper, and I just thought this was an interesting table that was in that paper. Although all these structures are made of wood, of course there are many species of wood, and that's one of the rich things about using wood, is that there's more variety, more variability in wood than there is in concrete and steel. So we can just talk about using wood, but actually the whole dimension of different species of wood is of interest in itself. In Romania, they actually used larch because we'd already used larch on a building in UK, which I'll be showing you more of. But previous gridshells used oak. Oak's a particularly resilient timber. And in Mannheim they used hemlock, and they used hemlock because it's very straight grain, although I would say actually it's quite a brittle timber, so it probably isn't the best timber to use for gridshells. And here's the structure that Dragos built with as a result of that workshop in Romania with a group of students. Okay, so the first large-scale timber structure was the Mannheim Garden Festival gridshell, designed by the German architect engineer Frei Otto, who is probably more famous for the Mannheim Olympics Stadium, which is now used by Munich Football Club. It's recently been refurbished. But his specialist area of work was tensile structures. He worked a lot with models. So he would make models, and then they would be the basis of what he would then go to win a competition, and then work with engineers to turn them into real structures. This is a huge structure, and there really was nothing like it before, and there's nothing as big as it since. And he searched, so he started with a hanging chain model, and if you invert a hanging chain model has to be completely in tension. All the members in it have to be completely in tension, otherwise the chain wouldn't hang. So a hanging chain model, it is a structure that's 100% in tension. So if you invert a hanging chain model, you get a structure that's 100% in compression. That's under the self-weight of the structure. Actually, for wood, the self-weight, so this is a fantastic technique to use for a masonry structure, but it is a way of getting a geometry in timber, but is not as vital because timber is a lightweight material, and so actually the forces on a timber structure are more significantly from wind and snow than from the self-weight of the structure. But it's an interesting way to get a structural form. And he then needed to search the world for an engineer who could help him realize this structure. And he found Ted Happold, who at that time worked for Arup in London, and with the team in Arup, this building was realized in 1975. Really extraordinary building with some very interesting details, which actually derive to a very large extent from the sorts of details that he used on tensile structures. And the building is still standing. It was built as a temporary structure, but was so successful that it's never been taken down. As a temporary structure, the weatherproofing is not terribly great. And it has suffered deterioration over the years. But there's a strong move to refurbish this structure by engineers, particularly in Germany. This paper for the structural engineer, written by Ted Happold with Ian Liddell, is a very detailed engineering account of the structure, and it is a very important paper, I would say, in the development of timber gridshells. Ted Happold left Arup in 1975 and started his own company called Bureau Happold, and he started that company in Bath, and the team that he took with him to Bath were essentially the team who had worked on the Mannheim timber gridshell. So the office in Bath, the company Bureau Happold, actually became the repository for all the engineering knowledge that there was on timber gridshells. And Ted Happold died in the mid-1990s, but so 20 years after Mannheim, but there was always a strong desire to take that knowledge and use it on the right project to create another gridshell. And the first opportunity came with these little tiny structures that were built near Doncaster for a Millennium project. And it was just, they're landscape structures, very simple structures, but it was just a new opportunity to build some real prototype structures. Very small, so a tenth of the span of Mannheim, but using similar techniques. A lot of the details very similar to the Mannheim structure. Only 2 layers of wood, what I would call a single layer grid shell. I'll talk more about that as we go on, the layering of grid shells. Although very small, a lot of the details were taken straight from Mannheim, and they were actually extremely successful. And through building these, it really architecturally created a big impression, because nobody had seen structures like this for a very long time, and it really rekindled the imagination. At the same time, for the Hanover World Expo in the year 2000, Shigeru Ban had the idea of building a grid shell. The theme for Hanover Expo 2000 was sustainability, and of course Shigeru Ban is known for his paper structures, and he wanted to build a very lightweight, completely demountable structure, something that could be put up quickly and taken down with all the components capable of being recycled. So even the foundations were simply boxes of sand held between scaffold boards, so the whole thing could just be taken down, absolutely minimal impact on its surroundings. Once again, a single leg gridshell, two pieces of two cardboard tubes, and the support shared between the gridshell and these glulam ladder arches. Just simple ties for the nodes. Really a fantastically successful piece of architectural design. This is the finished building, which had an incredible visual impact. But what this then did was show people a large scale gridshell structure, and because it was built in 2000, 25 years after the Mannheim structure, it had to be built following modern health and safety methods and within modern financial constraints. And so the construction techniques that were developed for this building actually moved the whole opportunity for building gridshell structures on a long way. At exactly the same time, and in parallel with the Mannheim gridshell, Bira Happold were commissioned by the Weald Down and Open Air Museum, which is in near Chichester on the south coast of England, a museum of historic buildings where they rescue and re-erect buildings from various places in the south east of England within the museum. And because they refurbish the buildings before they re-erect them, they actually need a workshop. And the very common thing to do in museums like this is actually to use historic techniques to build an oak frame workshop. That would be the sort of obvious thing to do, but the director of the museum said such a building is just a pastiche, and I want a really modern building. What's more, I want a modern building that's not like anything else in the country. And Edward Cullinan Architects picked up on this and picked up on Bira Happold saying we should do a gridshell, whispering in his ear all the time. And over a period of a few design workshops, the concept for a timber gridshell workshop came up. Not as big as Mannheim, sort of similar size to the Japan Pavilion, and a very similar shape to the Japan Pavilion. This woven mesh that is made really for fly screens to go over windows, mosquito screens, is a wonderful material for modelling gridshells, because it does exactly the same thing as a timber gridshell. Because it's woven, the nodes will rotate and you can manipulate it into a doubly curved shape. And it was very, very quick. We had a school student actually working doing work experience for us in the office in Bath, and he attended the first workshop and spent a week and built this model, which really does very closely represent what the building came to be. We spent a lot more time to very carefully make this bigger model using strips of wood actually really bolted together at the nodes, really as a way of rediscovering the sort of feel for how a timber grid shell moves into shape. This was actually made by two more students on work experience. Two students from Canada made this one in the Bureau workshop. And we made it very, very carefully, scaling the pieces of wood precisely according to their stiffness, and made it just big enough to go in the partner who was working with us on this project had a great big Mercedes estate car, and we scaled the model to be just the size that would fit in the boot of his car, so that we could then take it to the client, who then drove it around the country to raise money for his project. Hugely successful, and at the end of the project he bought this model, and it's still on display at the museum. So let's talk a bit more about the engineering detail of a timber grid shell. I know this is engineering, but I hope that even though it's a sort of engineering detail, you'll be interested in this, because it is the crux of why the timber grid shell is as it is. Here's the earth center grid shell, just a very simple two-layer structure, what I would call a single-layer grid shell. This can be bent into shape, and the node can be fixed because it just has to rotate. The Mannheim grid shell has two layers going that way, and then another two layers on top of that. So I would call that a double layer grid shell. It's got 4 layers of wood, but 2 layers going in one direction, 2 layers going the other direction. Why does it do that? Well, those 2 layers of wood, after they're manipulated into shape, are then locked together with a shear block, so that the 2 layers going in the same direction work together. And here is the wheeled and downland grid shell. Those timbers that lock the layers together are fitted in after it's bent into shape. So here it is just after it's been bent into shape, but no shear blocks in place. The dilemma with making a timber grid shell is that you want the timber to be flexible enough to bend, but stiff enough to resist the forces applied to it. This little equation, which is a very simple little equation, actually solves practically every structural engineering problem there is to solve. Really, if a structural engineer knows this equation and understands it, they don't really need anything else. Structural engineering is a very simple discipline. Everything is in this equation. That's the bending moment. In other words, the applied force to the structure. These are geometric properties. This is the moment of inertia, or second moment of area. This is the depth of the member, and this is the material property. This is the stiffness, the Young's modulus, and these two, the sigma is the stress that you get when you apply the bending moment as a result of it bending into a certain radius of curvature. So really everything that an engineer needs is in this one equation. So that's the stress, and the important thing to note here is that if you bend a piece of wood, then the stress that you get in that piece of wood is is dependent on the distance from the middle of the wood to its extreme fibre. If that, to bend it to a certain shape, so we're making a structure, so we're not bending it to a stress, we're bending it until it's curved into a particular shape. R is that shape, so when we've bent it, then R is what we've defined, what we want it to be, the radius of that curvature. So the bigger the distance from the centre of the piece of wood to the extreme fibre, the higher the stress. So to bend a piece of wood into a particular shape, we want that piece of wood to be as small as possible, because then that stress will be low. So if we take a piece of wood this thick and try and bend it into that shape, we'll have a huge stress. It'll take a huge force. If it's that thick, I could do it here with my hands. So that distance there, when in bending the shell into shape, wants to be as small as possible. On the other hand, when we apply a load to the wood, when it's in use, well then we want that stress that we get to be as low as possible. And the stress that we get when we bend it is a property of this value called the second moment of area. And that we work out from the width of the wood and the depth of the wood. So we're back to the depth of the wood, and the stresses under load can, from that first formula, be shown here. So the higher the second moment of area, the lower the stress. So here we want these values to be as big as possible. So how do we get a situation where the wood is flexible, in other words its depth is shallow to bend it into place, but deep when it is bent into place? Well, we split it into two halves and bend it with a shallow depth, in fact two shallow depths, and then we lock those two depths together and we get a bigger depth. Here we are, here's the two pieces of wood that we bend into shape with a shallow depth, and then we lock them together and we get so there's the depth of the wood when it's being bent into shape, and there's the depth of the wood after it's been bent into shape and locked together with the shear block. And by doing that, by locking them together, we get a second moment of area, a strength essentially, of timber that's 13 times bigger than the two pieces on their own, just by putting that shear block in. We get composite action. So that's really the key to the timber grid shell. When used in any sort of scale, we bend it with single layers and then lock it together after it's bent into shape to get a thicker layer. Using, I mean, these are these are 20 years old now, these drawings, but this was the very early days of having graphical output from computer analysis, and we could do the analysis of the bent form. And we're not recording, so if it keeps crackling, I'll turn it off and speak up. Still crackling, even though I've turned it off. Never mind. Knowing what the shape is going to be from the flat mat is hugely beneficial in construction. I haven't got time to talk about all the detail of that. This is probably more important to mention. I think this was something I learned working in Bureau Happel. Bureau Happel did a lot of innovation in structural engineering. Ted Happold had enormous confidence in the ability of himself and the people he worked with to do things that had never been done before. Something that I was taught in Bureau Happold was that when you're doing something very innovative, you have to gain the confidence of the team that you're working with. You have to gain the confidence of the client, you have to gain the confidence of the architect, you have to gain the confidence of the cost consultant, but more than anything, you have to gain the confidence of the constructor, the person who's going to build it. So here I am, 20 years ago, with the two carpenters, and what we've done is ask the carpenters to make the piece of grid shell that is curved more than any other part of the whole structure. Because when they looked at these drawings, they thought, well, can you really bend it to that radius of curvature? Well, by making a full-size piece of it, here's Steve Corbett with his boss Andrew Holloway, and Steve's saying, what, you're not going to bend it any more than that? That was easy. And from that point, they were our best allies for the project. And it happened, I did the same with concrete on another project, where it was a very complex precast concrete element, and we got the contractor to make it and erect it just as a single frame. And once he'd done it, he said, well, that's easy, of course we can do it. And I think that it's really worth emphasising. Get the contractor on your side when you're doing something innovative. Timber only grows a certain length. Why can you bend a timber grid shell into a complex doubly curved shape? Well, because the wood is sufficiently flexible to bend to that shape, and we made some very long pieces of wood using automated finger jointing methods, and then you can't transport a piece of wood 30, 40 on the next building 50 meters long, so they're brought to site, and then very simple traditional scarfing methods used to join them together. So we're making long lengths of wood using glued joints. There's the workshop. Mannheim, in the erection, pushed the shell up using a forklift, very on really not a terribly safe procedure actually. And what the Japan development did was introduce a scaffolding system with an adjustable prop using a Perry system. Perry is actually a formwork propping system. It has a very long adjustable prop. And here's the downland grid shell construction sequence as set out by the Perry Scaffolding Company. So it's a proprietary scaffold system, so the carpenters could actually move the scaffolding around, and it's a very carefully worked out procedure for, but in this case using gravity, so putting the scaffolding, setting it out high up, and then using the adjustable props to gradually, in a predetermined way, adjust the props so that the shell then moved into a curved shape. And actually gravity just took it there. Needed a little bit of help sometimes to just ease the diamonds together, but essentially there's the scaffolding going up. Here's the long pieces of wood being carried out. The carpenters, here's a nice practical thing. In carrying the timbers out, they marked a line on the ground which was a tighter curvature than any point in the structure. So every piece of wood, just as it was being carried out to the site, actually got proof tested. And then there it is set up, and now we see the scaffolding being altered beneath it, and the shell falling into its predetermined shape. So we, as I said right at the start, we start with a flat grid of standard components, just long straight bits of wood, and by manipulating the shell we can bend it into a very complex shell shape. Very calm construction process. You saw there were no cranes. There were birds making nests in the scaffolding at this time, actually, which we didn't disturb. And a small team of 8 carpenters and an engineer who did that work. Quite slow. It's not something that you can just get in and do very quickly. But if it can be properly programmed in, the client didn't actually mind how long it took to build this building, and I don't think that's necessarily so unusual. It did want to know more or less how long it was going to take. I think clients hate the being let down when halfway through a project is suddenly told it's going to take years longer. Okay, this construction process just to build the shell took 3 or 4 months, which is quite a long time to make that. But the museum was open, the museum had visitors coming, and they were watching the construction process, and everybody was enjoying it. It's clad with wood, polycarbonate windows, and there's the finished workshop. And even though the construction period is long, so here's the grid shell forming, 3 or 4 months. Actually, in terms of the whole project, by far the longest part of the project is the preliminary part. So the idea was in 1995. We got some initial funding from the Heritage Lottery in 1997 to develop the design. So this period is fundraising, is getting people interested in it. A short period doing the scheme design, having done the scheme design, then raising more money, and then appointing the contractor. So it's 1, 2, 3, 4, 5 years prior to starting the construction. So what's it really matter that it takes 3 months to build the shell, providing you know it's going to take 3 months to build the shell? And I don't think that's unusual, an unusual program for a project, actually. And there's been many papers written on this. So now, having built the diamond grid shell, we can then offer this as a solution to clients who otherwise wouldn't be open to such an innovative structure. The client on the Savile building is the Crown Estates, who run the Queen's property portfolio, a very conservative client. Most of their buildings are office blocks in London. So they would not have taken kindly to Wen-Shao's competition winning entry if we couldn't point to a building that was already constructed using the technique. Here's Wen-Shao's competition winning sketch, which shows an axis through Windsor Great Park and a floating curved shell structure. It virtually shows everything that there is in the building, I would say. So it doesn't. I think it's a very impressive sketch. Probably initially done on a napkin at a dinner with an engineering colleague of mine. But this is building it up, that sketch, into something a little bit more elaborate. Very early engineering ideas of how it would work out. We decided to use larch because okay, let's talk about this very quickly. The way that I think has become the standard way. There's variations on this, but the standard way for creating you have to know what you're able to bend the timber to, what creates an effective structural solution. But essentially you agree between the architect and the engineer a geometric surface, and once you have that surface, then you can lay a grid onto that surface. Once you've laid a grid onto the surface, then you can analyze that, and having analysed it, you can then specify the whole structure, and that's essentially how it's done. And in the analysis, it's hard to do a lot of development. The tricky thing is that you have to get the form right at the start. You have to use quite a lot of engineering judgment to get the form right, because there's such a lot of work in doing the analysis, and the shell is so much part of the architecture that it's hard to make changes. So there's a lot of experience and judgment goes into it, which is maybe why there aren't so many of these things built. But structurally, what one has is some stiff domes with this form of structure, with some tensile areas that hang between those stiff compression areas. There's some very nice development of the structural details on this building, which were done with the carpenter, who fortunately was the same carpenter that we worked with at the Downland Gridshell. So a carpenter who really knew what they were doing. Why was it made of larch? Well, because Windsor Great Park has an FSC sustainably certified woodland with magnificent larch trees in it. So very, very fine quality wood available from almost within sight of the building. Because we were using timber from the local woodland, and we knew exactly where it's coming from, we could test it, and rather than give it a structural class taken from the codes, we could give it our own class, which was this is Saddle Grade 1 and Saddle Grade 2, and we could describe it, and having tested it and done statistics on the results, we could say this is graded wood, and we know how strong it is, and we were able to use it very effectively, essentially using the better quality wood for the long timbers and the lower quality wood for the shear blocks where the stress was lower. We did prototyping again. In this case we had the same contractor, and it was more to give confidence to the client and to show the client what they were going to get. I think the client found it very hard to visualize just how big this building was going to be. Okay, there are lots of drawings of it, but actually building a bit of it in it. So this is a medieval barn, and here's a small section of the shell built to a size that enabled people to walk underneath it and really get a sense of how big it was going to be and what it was going to look like. One of the really significant things that came out of this was that this is spruce plywood, and the cost consultant wouldn't contemplate us using birch plywood, but when the client saw the spruce plywood, that immediately said, I don't like that. And we said, oh, you could use birch plywood, which is very much stronger, so much easier to use for from a structural point of view, and just that one thing alone was very beneficial. So here are the trees being harvested, cut into length, sawn into size, finger jointed off site, brought to site, and almost identical picture to the Downland Gridshell, but actually this is the workshop for the saddle building. So being spliced together, carried out in exactly the same way. In this case, built as a single layer grid shell and bent into shape. So here's the single layer, the one timber in each direction being bent into shape, bolted to an edge tube, and then the shear blocks were applied on top of that layer, and the next two layers applied on the top. That made the construction much easier. Here's the shear block, and it meant that the layers don't actually touch one another. It gives even more structural depth and gives a more open appearance architecturally. Masses of screws, very slow construction again, but very calm and very predictable. And rather than on Mannheim, it's really important structurally to give the shell stiffness in plane, so you have to brace it. On Mannheim it was braced with tension cables. On the Downham grid shell it was braced with extra bits of wood put across the diagonal. On saddle building, especially as we were able to use the birch plywood, we actually braced it with the plywood, and here's the plywood going on to brace the shell. And then on top of that, a rain screen of oak boards. There's a lot of discussion about what should the finish be. It has a raised seam aluminium roof over the top of the grid shell structure, but then to hide that, it has oak, which then I haven't seen it for about 5 years now, but be really interested because it's quite a polluted part of London. It's very near Heathrow Airport, but certainly initially, quite surprisingly, it gained a lovely silver colour. It would be interesting to see whether it's still managed to retain that, or whether you'd expect it to go a bit black because of the polluted air, but it actually initially went a beautiful colour, and that's what it's like inside. It's a raised, curvy plate, and architecturally it uses that, it expresses that very, very strongly. So I think that it really does follow the competition sketches. This is a tiny structure, but it's just an example of making a shell from start to finish, starting with this woven mesh to get a form, turning that into a structural model, turning the structural model into a physical model, and then creating a very small grid shell. In this case, using the same node detail but with an extension and putting a glass roof on it. So just showing that you can and using double cables as the bracing system. The place where there's quite a bit of research going on into timber grid shells at the moment is in the Polytechnic in Madrid, and I just found these images today. This is a shell that they've constructed in Santiago de Compostela, but it's the engineers in the department in Madrid who provided the engineering expertise, and they've actually they've done this is the culmination of quite a lot of engineering research they've done, which I think has really moved the understanding of timber grid shells forward. what makes this structure interesting is it doesn't have edge tubes. It has cross arches that it spans over, but they've worked to a further stage in understanding how the timber stresses. So it cantilevers forward over the top of these arches, and they've done a lot of work in developing an understanding of what the stresses are in the bent structure. So that's it. It's a little story of turning wood into something of higher value, but it's still wood. Thank you.